Hello everyone, in this video we will be discussing on the system design key concepts part 4, that is asset transactions. We will be covering what are asset transactions, what is atomicity, consistency, isolation and durability, and how these all four concepts are implemented in the database. So firstly, what is asset transactions? Asset transaction is the acronym of atomicity, consistency, isolation and durability. Consider retail scenario where we are ordering certain quantity of particular items, and while doing the payment, consider the payment got failed, but the quantities from the retail inventory has already reduced. If it happens, then it will lead that particular database system into an invalid state. So it is always necessary we should have implemented the asset transactions in the system. What is a database transaction? A transaction in the context of databases is a sequence of one or more operations. That is means in the previous retail scenario, if payment got failed, then it should not have reduced the quantity of number of items from that particular retail inventory itself. So these all steps will be considered as one transaction. Consider the bank transfer. In that, if we are transferring money from account A to account B, then the money should be deducted from account A and the money should be credited to account B. If these whole two sequence of transactions completes, then only it is considered as one transaction. But if one of these did not complete, and then it may result in partial updates or conflicts. So first one is atomicity. Atomicity is perform all the operations, otherwise do nothing out of those operations. And it can be how the database implements the atomicity. It implements through the transaction logs, that is write ahead logs, and the second one is commit rollback protocols. So first one is transaction logs. So this is the example of transaction log entry. So once that WL entry is safely on the disk, that is write ahead log entry is safely on the disk, the database proceeds with modifying the in-memory pages that contains the rows for both the accounts. And when the operation succeeds, then only the database marks that transaction ID 12345 as committed in the transaction log, and that newly updated balances for both the accounts will eventually get flushed from the memory to their respective data files on the disk. But let's say if the database crashes after that log entry is written, but before the data files are fully updated, then what that write ahead log entry does, it will provide a way to recover that. Once that restart happens, then the database checks firstly that while entry, and if the transaction 12345 was committed, then it reapplies that update operations to ensure that the final balances are correct in the data files. But let's say if the transaction had not committed, or it is like in progress before any particular failure happens, then the database would roll back those changes using that information in the log and leaving that table as the transaction did not happen itself. And second one is commit rollback protocols, and it is implemented by using the begin transaction and commit, and begin transaction and commit. Between these two, whatever we wanted to consider as whole transaction, those all steps will be written here, and if all are done, then only commit will happen. Otherwise we can do the rollback, and it can be manual, otherwise automated. Second one is consistency. Consistency, it ensures that any transaction will bring the database from one valid state to another valid state, and it never leaves it in a broken or invalid state. And it can be implemented in a database by using three ways. First one is database schema constraints, second one is triggers and store procedures, and third one is application level safeguards. Database schema constraints can be done by using different keywords like not null, unique, primary key check, foreign key check, check constraints. In this previous example, here let's say if you wanted to check the quantity should not become 0. If it becomes 0, then it should not perform that operation. So that we can do by using the check constraint, that never the quantity should become 0. Here if we are reducing the 10 from the existing stock quantity, then it will become 0, so it will not allow this operation to happen as we had implemented the check constraint. Second one is triggers and store procedures. It can automatically check additional rows whatever we wanted to have whenever particular rows are inserted, updated or deleted. And also we can implement the store procedures which can contain logic to validate the data before we are committing. And third one is let's say if you wanted to perform any business scenario then at that time we can have a application level safeguards. Third one is isolation. It ensures that the concurrently running transactions do not interfere with each other's intermediate state. But let's say if the isolation do not maintain, then it may result in three concurrency anomalies. First one is dirty read, second one is non-repeatable read, and third one is phantom read. Dirty read is like, let's say transaction A reads the data that transaction B has modified but not yet committed, and let's say then the transaction B rolls back, then transaction A ends up holding an invalid or that dirty value that never truly existed in the committed state. Second one is non-repeatable read. Let's say transaction A reads the same rows multiple times during its execution but sees different data because another transaction is updating or deleting that rows from the database. Then it will lead to non-repeatable reads. Third one is phantom read. It is like transaction A performs a query that returns a set of rows, and another transaction in between inserts, updates, or deletes rows that matches its query conditions. Then if A reruns again the query, then it may see a different set of rows, that is phantoms. That is phantom read. And second one is isolation levels. Then database typically allows you to choose an isolation level which balances the data correctness with performance. And higher the isolation level provides a stronger data consistency, but it can lead to the performance issues. And we have four common isolation levels. First one is read uncommitted, where we saw, let's say consider two transactions. First transaction A updates the balance from 10,000 to 5,000 but doesn't commit, and then transaction B comes and it reads the balance and sees as 5,000, but in between transaction A rolls back and reverting again balance to 10,000. Then transaction B has already read that uncommitted or the dirty read of 5,000. Second one is read committed. In this it will prevent the dirty read. Consider the transaction A reads balance of 10,000. Then transaction B deducts that 5,000 and commits. Then again transaction A will read and that will be reading the value as 5,000. So it will restrict the dirty reads. Third one is repeatable read. It prevents dirty reads as well as non-repeatable reads, but phantom reads may occur. For example, consider transaction A reads 5 available concert tickets, and transaction B adds 3 more tickets and commits, and then transaction A reads again. Then 8 tickets appear. So it is again and again reading. It is repeatable read. And fourth one is serializable read. What it does, it is the highest level of isolation where it will prevent all three concurrencies like dirty reads, non-repeatable reads, and phantom reads. How it is implemented, let's say transaction A queries tickets and sees 5 available, and transaction B comes and it adds 3 more tickets and commits. And when transaction A tries to query again under serializable, it sees the original 5 as if B happened after A and hits a serialization error and is forced to retry. In this way it is serializable will be done. And how database implements the isolation? By using locking, MVCC, and snapshot isolation. Locking is like rows or tables are locked so that no other transaction can read or write them, but it can lead to blocking or deadlocks. Second one is MVCC. It is like instead of blocking reads, the database keeps multiple versions of a row. It will reduce the lock contention but requires carefully managing row versions. And third one is snapshot isolation. It is form of MVCC itself, where it prevents the non-repeatable reads and dirty reads, but phantom reads may still occur unless the isolation level is fully serializable. Fourth one is durability. It ensures that once a transaction has been committed, the changes it made will survive even if the any failure occurs or system crash. And it is implemented using 3 ways. First one is transaction logs. It is like write WL entry. Firstly write changes to the log, then commit the transaction and apply changes to the main data files. Second one is replication. It is like synchronous replication and asynchronous replication. And third one is backup, by taking the full backup of a system, or taking incremental or differential backups, or having the offsite storage. So by using all these techniques we can implement the durability. Thank you.